Section: Introduction. We, in our study, delve into the complex world of understanding discourse, a key challenge in the field of natural language processing, NLP. This involves not just looking at individual sentences but understanding how words and phrases relate to each other across sentences, how information is carried over in conversations, and recognizing specific patterns in discourse like missing information that needs to be inferred. Large language models, LLMs, have been a game changer in this area, showing impressive abilities in understanding language and knowledge about the world. Their success across various tests has quickly made them a focal point of both academic and industry research. However, as LLMs continue to grow in size and sophistication, it's equally important to evaluate their abilities thoroughly. This means developing detailed methods to test how well they understand language, including the nuances of discourse. But there's a gap here. Recent LLMs, despite their advancements, have been tested on a limited range of benchmarks, often overlooking the importance of evaluating them on discourse-related tasks. This oversight limits our understanding of their true capabilities in language comprehension. To tackle this, we propose a comprehensive evaluation using a variety of benchmarks and datasets that cover different aspects of language understanding, including common sense, sentiment analysis, and more. Yet, we notice that current benchmarks don't fully test for an understanding of context, which is crucial for tasks like sentiment analysis. Moreover, the growing size of LLMs has led to increased computational and storage demands, making it challenging to deploy these models on personal devices. To address the issue of size and efficiency, model compression techniques, like 3-bit quantization, have been explored. These methods can significantly reduce the size of models with minimal impact on performance. However, the effectiveness of these compressed models, especially in understanding context, hasn't been thoroughly evaluated, and there's a lack of linguistic analysis to pinpoint where these models might fall short. In our paper, we focus on evaluating LLMs on a benchmark specifically designed for understanding context, using various discourse understanding datasets. We look at models of different sizes and those that have undergone compression to get a clearer picture of their abilities in context understanding. Our contributions include introducing a new benchmark for context understanding, evaluating a range of LLMs, and analyzing the impact of compression on their performance. Related to our work, the concept of in-context learning, ICL, is gaining traction. It's been shown that LLMs can perform better on various NLP tasks when given a few examples as prompts. Our study also touches on model compression for LLMs, which includes techniques applied during training, fine-tuning, and after training. Among these, quantization has shown promise, and we specifically explore its impact on context-aware tasks in our work. Section Summary. The introduction section discusses the importance of discourse understanding in natural language processing and the growing significance of large language models, LLMs, in comprehending language and world knowledge. It also highlights the need for robust evaluation methodologies to assess the capabilities of LLMs, especially in context understanding, and the challenges related to the computational and storage costs of large models. Additionally, it introduces the paper's contributions, including the introduction of a contextual understanding benchmark for evaluating LLMs and the evaluation of post-training compressed models in in-context learning settings. The related work section briefly mentions the growing importance of in-context learning evaluation and model compression techniques for LLMs. Section: Task Selection and Design. We've put together a benchmark for understanding context that includes 4 different tasks, using 9 datasets in total, as shown in one of the figures in our paper. Let's dive into each task and the datasets we've chosen for them, as well as the specific prompts we've designed for evaluating models through in-context learning, ICL. Starting with co-reference resolution, this task is all about understanding the connections between various parts of a text to grasp its overall meaning. It's a key test of a language model's ability to pick up on references and the context within documents. We've chosen 2 datasets for this, WSC 273 and OntoNotes 5.0. WSC 273 is based on the Winograd Schema Challenge and involves figuring out the referent of an ambiguous pronoun from two options. Onto Notes is a richly annotated corpus covering a range of linguistic features, including CO reference, and is widely used to train models on this task. However, the traditional training methods don't work well for generative models in ICL settings. Recognizing this gap, we've come up with a new approach that involves a multiple-choice task where the model has to pick the correct referent from given options. We've designed prompts that include instructions, a highlighted mention in the text, a list of possible referents, a question to focus the model, and a keyword for the answer. We've tested various prompts and chosen the best performing ones. To evaluate, we use the official metrics from the CONLL 2012 shared task, which include 3 CO reference metrics averaged into a CONLL-F1 score. Next, we have dialogue state tracking, DST, crucial for models involved in task-oriented dialogue. It involves keeping track of key information through the conversation. We use the multi-WAS dataset as an example, where a user sets constraints for finding a restaurant. The DST output is organized as slot value pairs. Previous studies have shown that ICL can perform well on this task, even compared to traditional fine-tuning methods, though these studies often didn't include smaller models. We've adopted a simplified ICL approach for testing on multi-WAS v2.2, with prompts that include relevant domain knowledge, instructions, the previous dialogue state, and the current conversation turn. We measure performance using joint goal accuracy. For implicit discourse relation classification, we focus on how different parts of a text connect to form a coherent message. We use the PDTB3 corpus, which annotates implicit relations between text segments. This task is challenging because it requires a deep understanding of linguistic nuances, and we've turned it into a multiple-choice question with 4 options representing different types of discourse relations. The prompt includes an instruction, a brief description of each relation type, the context with 2 segments, a question with answer options, and a trigger word. We assess performance based on accuracy. In summary, our benchmark covers a wide range of tasks designed to test models' understanding of context, from resolving references and tracking dialogue states to classifying discourse relations. We've tailored our approach to suit in-context learning, with carefully designed prompts and evaluation metrics to accurately measure model performance across these diverse tasks. Section Summary. The section, Task Selection and Design, introduces 3 tasks for contextual understanding benchmark: CO reference resolution, dialogue state tracking, and implicit discourse relation classification. For CO reference resolution, the authors propose a novel multiple-choice task design to evaluate models on resolution, using official evaluation metrics from the CONLL 2012 shared task. In dialogue state tracking, the authors adopt a straightforward and simplified ICL approach and test it on multi-WAS v2.2, reporting joint goal accuracy, JGA, for evaluation. Lastly, for implicit discourse relation classification, the authors convert the task into a multiple-choice question and experiment with classes as options, evaluating each model's performance on this dataset using accuracy as the metric. Section: Query Rewriting. We're discussing the process of query rewriting in our paper. Unlike document-based CO reference resolution, which deals with identifying references within documents across various genres, query rewriting focuses on a different aspect. It aims to rewrite the last user utterance in a conversation into a standalone statement that doesn't rely on the conversation's context for its meaning. This is crucial because it challenges the model to understand and resolve references or fill in missing information, known as ellipsis, without needing the dialogue context. We've included 5 datasets in our benchmark to test this: Mudoko with query rewriting annotations, QRECC, INCAR, GECOR, and Canard. These datasets cover a wide range of dialogue genres and domains. We experimented with different prompts to fine-tune models and shared the results of the best-performing prompts. To evaluate the quality of the rewritten queries, we used metrics like blue and rouge, which are standard in previous research. For our experiments, we used a setup with 8A100 GPS and tested 3 families of models. For smaller models, we used opt models ranging from 125 million to 2.7 billion parameters. For mid-sized models, we chose Llama, which has models from 7 billion to 65 billion parameters, because they've shown better performance in previous studies. For the largest models, we used GPT 3.5 Turbo. We tested each model in 5 different scenarios: 0-shot, 1-shot, 5-shot, 8-shot, and 10-shot, randomly selecting examples for the few-shot scenarios. Our findings show that as models get larger, their performance improves, but pre-trained models still lag behind fine-tuned models in most tasks. When it comes to CO reference resolution, larger models do well on simpler tasks but struggle with more complex document-based CO reference resolution. The gap between in-context learning and fine-tuned models suggests that without specific examples, large language models have difficulty forming CO reference chains. In dialogue state tracking, opt and Llama models fall significantly behind GPT 3.5, indicating they struggle to keep up with the conversation and extract key information, even with several examples provided. Our analysis found that errors often occurred in identifying slots or predicting incorrect values in slot value pairs, with only GPT 3.5 reaching the performance level of fine-tuned models. For implicit discourse relation classification, we saw an improvement in scores as model size increased beyond 7 billion parameters. However, even the best-performing large language model, GPT, was significantly outperformed by the state-of-the-art fine-tuned model, with a 32% drop in accuracy. This suggests that models have difficulty distinguishing between different types of discourse relations. In query rewriting, there's a significant performance gap between small and large models. Smaller models, like OPT125M, couldn't even complete the task. Errors included generating a new sentence instead of rewriting, choosing the wrong part of the conversation to rewrite, or simply copying the last user utterance. These errors decreased as model size increased, but the best results from in-context learning were still far from those of fine-tuned models. Interestingly, OPT 2.7 billion performed as well or better than Llama 7 billion on multiple datasets, which contradicts findings from other tasks where Llama outperformed opt. Overall, our analysis shows that while small models can grasp some context and follow instructions, they perform worse than random guessing on classification tasks. Larger models are needed for generative tasks like query rewriting, where they have the freedom to generate content. However, fine-tuned models still significantly outperform pre-trained models, highlighting the potential for improving large language models' understanding of context. Section Summary. The section discusses the importance of incorporating CO reference resolution and ellipsis understanding into the benchmark for evaluating context understanding. It introduces the task of query rewriting, QR, in conversation and presents the results of different model families on various datasets, highlighting the performance improvement with larger models. The comparison reveals that while smaller models show some level of context understanding in tasks with structured outputs like CO reference resolution or dialogue state tracking, larger models outperform them in generative tasks like query rewriting, indicating the potential for improving language models' competence on context understanding tasks. Section: Model Compression Technique. In our study, we looked into how well large language models, LLMs, can understand context when given instructions in an incremental context learning, ICL, setup. We specifically examined models that had been compressed using a technique called GPTQ. This technique is a one-time process that reduces the model's size after it has been fully trained. It works by simplifying the model's weights in a way that doesn't need much information to be effective, allowing the model to take up to 80% less space in memory and on disk compared to before it was compressed. When we tested these compressed models, we found that GPTQ could shrink the model size significantly, down to 3 bits, without losing much ability to perform a variety of natural language processing (NLP) tasks. These tasks included multiple choice questions, answering complex questions, and completing stories. However, it was uncertain if these models would still be good at understanding context. Our tests showed mixed results. In some tasks, the performance drop was minor, about 1.7 percentage points, but in others, the drop was more noticeable. Interestingly, when comparing the compressed version of the Llama model with 30 billion parameters, 30B, to the original version with 7 billion parameters, 7B, the larger, compressed model did better across all tasks, despite both models having similar storage and memory needs. This was especially true for certain tasks where the 30B model showed significant improvements, suggesting that the benefits of having a larger model can outweigh the downsides of compressing it. We also did a deep dive into how these models perform on a task called query rewriting, which is important because it involves generating new text based on given instructions. This task is unique because it's not just about choosing the right answer or filling in the blanks. It requires the model to creatively rewrite queries. We compared two families of open-sourced models, Opt and Llama, and looked at how compression affected them. Our findings were that Llama models generally did better than Opt models, especially at larger sizes. However, the performance on the query rewriting task didn't always follow this pattern, suggesting that we can't declare one model family superior based on just a few tasks or model sizes. In our error analysis for the query rewriting task, we identified two main types of mistakes the models made. The first type was failing to rewrite the query properly, often just repeating the last query. The second type was treating the task as a simple language modeling exercise, where the model would give a response to the last query without properly addressing the task's requirements. Our analysis showed that the larger, uncompressed model was better at avoiding these errors than the smaller one, but compressing the model to 3 bits did increase the number of the first type of error. However, the compressed model still did a decent job at the task, suggesting that compression can preserve the model's ability to handle such complex tasks to a certain extent. Overall, our study suggests that using larger, compressed models could be a good strategy for deploying LLMs in real-world applications where there are limits on storage and processing power, especially since the larger scale can mitigate some of the downsides of compression.